Math 2414, representing functions as power series, video 2. First example, direct use of geometric series. Or we could say the very useful series that we saw previously. The very useful series being 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n when the absolute value of x is less than 1. But if you want to think about this a little bit more generically from a geometric series perspective, we can think of it as a over 1 minus r equals the sum from n equals 0 to infinity of a times r to the n, where the absolute value of r is less than 1. In fact, I think I'd actually like to focus a little bit more on this one because since we're going to be building series out of functions, and the first term won't always be 1, it will be important to know how to build your function series like this. So I think we're going to go with that one instead of the one that's currently right here. They're both good, don't get me wrong. This one's a little restrictive in my opinion. So we're going to make ample use of a over 1 minus r is equal to the sum of n equals 0 to infinity of a times r to the n when the absolute value of r is less than 1. So how do we do that? Well, if we're going to build series out of functions, then we need to be able to make a correlation between the function that we have and this sum over here, which we can revert back into its series by looking for similarities between the two and reconciling the differences. For example, structurally speaking, both things in blue rectangles are fractions with a single term on top, a binomial on the bottom that both start with a 1. But this guy has minus something, whereas this guy does not. That's an easy problem to fix. All you have to do to turn a plus into a minus is to rewrite the plus as minus a negative. And by rewriting that as minus a negative, now we have more structural similarity between the function whose series we're looking for and the sum of a geometric series. In fact, we can make our identifications now. The number on the top represents the first term. The number being subtracted from the 1 in the denominator represents the ratio, which in this case is negative x squared, which means that our function can be set equal to the following sum. The sum from n equals 1 to infinity of the first term times the ratio raised to the nth power if the absolute value of the ratio, which in this case is negative x squared, is less than 1. Now, does this end the problem? Well, sort of, but not really. Sort of, but not really for 2 reasons. Number 1, I'd like this sum to look a little bit more like a power series, meaning we want a sum of a coefficient times x to some power. We kind of have x to a power, but not really. We have negative x squared to a power. So we're going to try to manipulate our current sum so it looks a little bit more like a power series. And secondly, this needs to be solved. We need an interval for x, not an interval for negative x squared. So let's take both of these over to the next page and see if we can address both of those issues. Our current sum is the sum from n equals 0 to infinity of 1 times negative x squared all to the nth power. And the interval is going to come from solving the inequality. Let's put it over here. Negative absolute value of x squared is less than 1. All right, let's start by manipulating the sum so that it looks a little bit more like a power series. Basically, what we want to do is get the x as close to by itself as we can. Well, the first thing we need to fix is the fact that the x has a negative on it. And by the way, why am I dragging this 1 times around? It was only sitting there because it was the first term, but multiplying by 1 is kind of easy to pull off. So we're going to lose that 1, and at the same time, we're going to split the negative x squared to the nth power as a negative 1 to the n times an x squared to the n. Just unmultiplying negative 1 times x squared. And I'd really like x to a power, not x squared to a power. That's also easy to fix. All we have to do is multiply the 2 times the n and get x to the 2n power. Now, granted, that's not x to the n power, but really when you want to represent a function as a power series, that's what you want to get. You want to get x to some power, whether it's n, 2n minus 1, 3n plus 17 is actually quite irrelevant. You just want to get the x with a power on it. But what about the interval of convergence? What about solving the absolute value of negative x squared is less than 1? Well, since absolute value turns negative things positive and x squared is kind of already positive, we could do that. We could lose the negative. Now, some common sense might prevail here, Some common sense might prevail here that x is going to be between 1 and negative 1. Technically speaking, when you solve absolute value less than 1, your next move is to sandwich this between negative 1 and 1. But if I square a number between negative 1 and 1, it's going to stay between negative 1 and 1. If you were to think about this from a graphing perspective, here's the graph of y equals x squared, or y equals x squared. We want to know when x squared or y is between negative 1 and 1. So here's 1 and here's negative 1. Here's the portion of the graph between negative 1 and 1. What are these x values? Well, they're also negative 1 and 1. So however you slice it, when you solve this, you get x's between negative 1 and 1. So our conclusion, therefore, 1 over 1 plus x squared will equal the sum from n equals 0 to infinity of negative 1 to the n, x to the 2n, for all x in the interval negative 1 to 1. In a geometric series, you never pick up the endpoints for convergence, but it is something we're going to have to consider here in just a little bit. But in general, for a geometric series, you don't. Oh, by the way, you could also say this. It's been driving me crazy not writing this all semester. But that symbol, that little E-looking thing, is a symbol for the phrase is an element of. It states a relationship between a single value and a set of values. In this case, the single value being an x, the set of values being the interval from negative 1 to 1. I'll probably sneak that in a little bit more because it's my instinct to write that as opposed to not write that.